Hello, quick demonstration of modulus functions in the MEI C3 syllabus, and I'm going to use the June 2013 question 1 as an example because it does both parts of what you might be asked to do. So first thing as ever, we read the question. Fig 1 shows the graphs y is the modulus of x, there we go, and y equals a times the modulus of x plus b, there we are, where a and b are constants. Okay, the intercepts of y equals ax, a to the modulus of x plus b in the x with the x and y axes are at -1, 0, that's that point there, and 0.5, so that's that point there. So question 1, find a and b. That's Raymond 1. Okay, well, I would always start this by looking at the bottom of the V. There's the bottom of the V and seeing what's going on. And we know, excuse me, there we go. We know that the bottom of the V here, the bottom of the V, this point here at the bottom of the V is -1, 0. And we can substitute that in to our equation. There it is, that's our equation. Substitute those values in, so 0 equals a -1 plus b, which means fairly obviously to us that -1 plus b must equal 0, therefore b must equal 1. Yeah, that's the easy one for us to find. And then we're going to, having done that, we can find a point on the one of these two V lines, and therefore find the gradient from that, which is going to give us our A. And we know that one of the points here is 0.5 rather. So here we've now already found what a B is, so I'll put that in here. Our starting position, y equals a times the modulus of x plus 1. Then we're going to substitute in, well, our y value is going to be 1/2 a times the modulus of 0 plus 1. Well, we can see that that's a times 1, and therefore a equals 1/2. Okay, so therefore we can write our equation of this function as being y equals 1/2 of the modulus of x plus 1. That's the first question we've been asked. Okay. What we're being asked to do in the second part, find the coordinates of the two points of intersection. They're telling us 2 points of intersection of the graph. So let's have a look. We can quickly see that there's one over here and there's one there. But what I'm going to do, and we'll bear that in mind to check our answer, but what I'd like to teach you is to look at this as ranges. And at each of these points here, the bottoms of the V's, our function changes from the left to the right in terms of the straight line, isn't it? It's on one straight line to the left here, and it's on a different straight line to the right. And therefore, the best way to look at it is to split that function up so that we've got straight lines in these ranges. So there's one change there at -1 for the straight line, the full line, and there's one change here at 0 for the dotted line. Yeah, so in effect we've got three ranges we're working in. Yeah, x is less than -1, this mid-range of -1 to 0, oops, my pen loves doing that today, and finally of an x is greater than 0, isn't it? So what I'm going to suggest to you that you do is you actually do the calculations of finding the roots split into these three ranges. So we know that a critical point there is -1 and the other one is 0, and therefore in this range x is less than -1, in this range x is greater than -1, less than 0, and here x is greater than 0. Yeah, and what I'd like you to do then is to work out what form each of these functions is taking, what straight line, a linear form is it taking in this range. So here our first function was y is the modulus of x. And our second function here that we're going to compare it to is y is a half of the modulus of x plus 1. Okay, we're going to work out what straight line's operating in each of these ranges. So when x is less than minus 1, this function is going to be y equals minus x. It's going to be our linear relationship. And when x is between minus 1 and 0, then our y here is also going to be minus x. And in this final region where x is greater than 0, then the modulus means that we're going to be working with a linear function y equals x. Okay, now let's look at our second function here. And when when x is less than minus 1, this function is going to be linear minus a half x plus 1. There we go. In this mid-range here, y is going to be equal to, now we've gone greater than minus 1 with the other side of the v, so this function is going to be a half of x plus 1. Yep, note sign change. And finally, in this top range, again, x is greater than minus 1, so again, y is half of x plus 1. You happy with that? Now we're just going to solve simultaneous equations and look at our answers. So for the first one, minus x, we can get rid of a y quickly by just equating, can't we, these two functions? So here we've got minus x is minus a half times x plus 1. If we expand the brackets, we're going to have minus x equals minus a half of x minus a half. There we go. So our next line here is if we add x to the half here to both sides, we can have minus a half of x equals minus a half. And in those circumstances, we can see that x is 1. But there's a problem, because that's not within our range, because we started with x is less than 1. Yeah. So it's not in range, outside range. So it's not a solution. Yeah, it had to be within the range. Solution. So we can get rid of that one. Yeah. Let's have a look at the middle one. Our middle equation here. Again, equating through y, we've got minus x, therefore equals a half of x plus 1. If we expand the bracket in the next line, we've got a half of x plus a half. In the next line, therefore, if we take away minus half x from both sides, we've got minus 3 over 2x equals 1 half. So our next line would be minus 3x equals 1, therefore x equals minus 1/3. And minus 1/3 is in the range that we started off with, hasn't it? It's being minus 1 and 1. So that's a valid solution. There we go. Valid solution. And we also know that if x equals minus 1/3 from our top equation, y equals minus x, which therefore will equal plus 1/3. So our solution point is minus 1/3 plus 1/3 xy. There we go. Let's go on to the next one, range. Here's our final range. In this one, y equals x, and y equals a half of x, so we'll just plus 1 in the brackets. So here we go. We're going to equate and expand the bracket again. I would recommend you do this relatively slowly so you don't make a mistake in the exam. Cancelling out a half of x, we end up with a half of x on this side equals a half. Therefore, x equals 1. And x equals 1 is in this range, isn't it? Yeah, because x has just got to be greater than 0 in this range. And also y equals x from our first equation up here. There we go. Yeah, y equals x. And therefore, it will equal 1. Y will equal 1. And therefore, our point here is 1 and 1. And if we want to, we could just go back up and check on the screen. That makes sense, doesn't it? That this one here is minus 1/3 plus 1/3 will be the point. Yeah, that's going to be minus 1/3 plus 1/3. That one. And this one here is going to be 1, 1. I would recommend, if you're in any doubt, that you substitute your value of your x and y back into both equations and verify that you've got a correct answer. Okay, finally, here are my quick notes, key learning points, summary for you. Modulus function gives us the positive, the absolute value of x here. Graphically, this looks in these curves, these functions have the shape of a V. It could be either a V with the point down or a V with the point up. And the important thing is that this A here tells us where the bottom of the function is, where the bottom of the V is, yeah, because that's the point where x equals A. This is going to equal 0, isn't it? If you're asked in a question to find the intersection of the modulus of two modulus functions, I would suggest you go and solve it range by range. Check that the solution you've got is within the range it came from. If not, it's not a valid solution. Draw a sketch if there isn't one in the question, so you know roughly where they are, the answers. And if any doubt, check your answers by substituting your answer into the equations and check that they work and the answers are consistent. Hope that's of use.